All right. So now we're going to work on reducing fractions. So if you remember, reducing fractions, all we do is divide by a common factor, right? So for example, if I have, like, let's say 4 over 6, then 4 and 6 have a common factor of 2. So I can divide the numerator and denominator by 2, and that gives me 2 over 3, right? So essentially, the reason we can do this is because dividing by 2 over 2 is the same as dividing by 1, right? And dividing anything by 1 keeps it the same, right? Keeps the same value. So essentially, when we're dividing fractions, what we do is we keep the same value while changing the appearance, okay? So it's kind of a cosmetic change, not a value change, right? It's kind of like, no matter how much makeup or whatever type of clothes you wear, you're still the same person on the inside, right? Same with reducing fractions, right? Same value, just the appearance changes. Okay, so it's a fashion change. All right. So anyway, back to back to the math. So we have a is not equal to 0, c is not equal to 0. You'll see that a lot of times in standardized tests and things like that. That's just basically saying that the denominator can't be 0, right? So we're assuming that, or in this case, they're stating that a and c cannot be 0. Otherwise, there'd be kind of a loophole there where we could say, well, if a was 0 or if c was 0, this, would be undefined. And so they're just basically closing that loophole. Okay. So basically here you can see that a is the common factor, right? And so what we did is we divided by a in the numerator and denominator, and those a's canceled out, and then we ended up with b over c, right? Or you can think of it as the a here canceled out with the a here, right? So you can think of it either way. All right. So reducing rational expressions. First thing we want to do is factor the numerator and denominator completely, right? The reason we want to do that is because we want to be able to see, just like we did with a, we want to be able to see what those factors are, right? If we can see what the factors are, then we can identify common factors and easily reduce. If we don't factor them out, it's hard to tell what the factors are, right? Especially with polynomials. And so that's why we want to factor everything completely. Then we'll be able to see what we can cancel out. And that's the fun part, is canceling stuff out. These are fun problems because you get to eliminate things and kind of get down to some simplest form. So number 2, divide the numerator and denominator by the greatest common factor. Okay, and basically that's what we talked about. Like here, dividing by a, here dividing by 2, right? So once we factor everything out, then we can identify the greatest common factor and divide by it. Okay, and we want to divide the numerator and the denominator. Don't forget to do both. All right. So, and just little kind of terminology here. Dividing the greatest common factor is often referred to as dividing out or canceling the GCF. Okay. All right. So let's see some examples. So number 8. Now number 8, you can think of this a couple different ways. One thing is, if you already know the GCF, you can just reduce by that and divide by that on top and bottom, either mentally or on paper. But let me just show you one thing we can do here is we can prime factorize this, right? So we can break 30 down to 3 times 10, and 10 is 2 times 5, right? 42 is 6 times 7. You can break this down a lot of different ways. That's 2 times 3. So then what you can do is you can cancel out the common factors. So like 2 and 2 cancel out, 3 and 3 cancel out. So all we're left with is 5 and 7, right? And so 5 over 7 is our final answer. Now, in order for that to work, you have to get it down to prime numbers. If you don't narrow it down to prime numbers, you could miss some things. All right. So, and that kind of gives you a sense of why it's important to get down to factors, because then you can see what the common factors are. All right, so let's try number 9. So I want to factor the numerator and denominator completely, right? So in the case of the numerator here, x squared minus 9, we can factor that to be, that's a difference of 2 squares, right? So it'll x here, numbers we can multiply, or the square root of 9, excuse me, is 3. Then we get a plus, and we get a minus. All right. Then on the bottom, here we have a GCF, right? 6. So remember, always check for a GCF first. And then we get x plus 3, right? Because I'm dividing this by 6 and this by 6 to get my inside values. All right. So now what do we have in common? Just a matching game, right? We have x plus 3 on top and on bottom, so we can cancel those out. Okay. And so what we end up with is x minus 3 on top over 6. Now, here's a tricky thing. It's very tempting to want to cancel these out, right? Like 3 over 6. Oh, yeah, 3 goes into both. We can divide by 3. But whenever you're adding and subtracting, whenever you have a polynomial, right, like a binomial or more, it's a package deal. You can't cancel out the 3 without canceling out the 6, right? Or excuse me, you can't cancel out the 3 without canceling out the x. Those are one package deal, okay? So be careful with that. Don't try to over reduce, okay? All right. So number 10. So first thing, we'll factor the numerator. So here I see I have a GCF of 3. I'm just going to factor that out above just so I can don't have to rewrite everything more times than I need to. Okay, so I factor that out. So now I have a simple quadratic, right? I have a 1 here. So that's why we checked for a GCF, right? Before it was complex. Now it's down to simple. And so I want to find numbers I can multiply to get 2 that I can add to get 3, right? So I'm going to bring the 3 over, open up parentheses, numbers I can multiply to get 2 that I can add to get 3. Those are 2 and 1, right? So then this tells me the sign of the bigger number. So the 2 will be positive. And then this tells me if the signs are the same or different. Positive means the same, so they're both going to be positive. All right, now let's deal with the denominator. So I see a GCF here, so once again, I'm just going to do it right below, just to save myself having to write a whole another step. And so now I can see, okay, well, this is a difference of squares, right? So I'm going to bring 2 out to the front, open up 2 sets of parentheses, x here, the square root of 4 is 2, so I'm going to have a 2 here, 2 here, and then a plus between one, minus between the other. All right, so once again, we're just playing a matching game. So x plus 2's, those are the same, they cancel out. I don't see anything else that's the same. There's some things that are tempting, like it's tempting to want to say, okay, well, why can't we cancel out these x's? But remember, this is a package deal. The x and the 1 go together, so it has to be an x plus 1 to be able to cancel it out. The same thing with, yeah, I guess that's it in this case. But watch out for here, you can't cancel these out, right? That would not work. X plus 2 and x minus 2 are not the same thing, right? And so watch out for that. All right, now, here it says, in example 10, there's 4 different ways to write the answer. We usually give the answer with the denominator factor and the numerator not factored. So denominator factored and the numerator not factored. So for example, here we would probably leave it as 3x plus 3 by distributing here, but leave the denominator as 2 times the quantity of x minus 2. Okay. So, but you could also simplify this. You can leave them both of them simplified like this. This would be okay as well. All right. So there are a lot of different ways to express the answer sometimes, but just make sure that you have it completely simplified. And so make sure you factor at some point so you can make sure you check to see if everything's simplified.